All right, this video is going to start a small series of videos, just like we did with the superposition principle. We are going to make a few videos here on the Annihilator approach for undetermined coefficients. So I'm going to jump all the way down in the textbook to the problems that actually have us solving some equations here. And I'm going to take them case by case. So case one is I'm just going to use the regular differential operator that I'm going to call capital D here. And so I'm going to try to make the right-hand side equal to a 0. So let's go ahead first and let's write this auxiliary equation where this is d squared minus 9 is equal to 54. And I want to take the derivative of both sides. So when I do that, that's like multiplying by d here. I have d times d squared minus 9 is equal to 0. So that gives me an equation on the left-hand side that factors into d plus 3, d minus 3. And I get a d equals 0, or d plus 3 equals 0, or d minus 3 equals 0. So d equals 0, or d equals -3, or d equals 3. Really, capital D here is taking the place of my m that was in my auxiliary equation before. It's acting in the same way. So I have y, the total y is going to be equal to a plus b e to the -3x plus c, let's call this c1, c2, and c3 e to the 3x. So let's call them a, b, and c for right now. It really doesn't matter. I'm going to compare and see what parts are the same. So coming back up here, just looking at this part here, that I would have made my auxiliary equation with m and made this m plus 3 times m minus 3 equals 0, m equals -3, or m equals 3 is going to be yc is c1e to the -3x plus c2e to the 3x. So anything that's already in yc, I'm going to eliminate from my y to make my yp is just going to be a constant a. That would have been what we would have guessed here anyways. And then we move on with our method like we did last time. So that means yp prime equals 0, yp double prime is equal to 0, which means that I have 0 minus 9a is equal to 54. A equals -6. And so we have our y is going to be equal to -6 plus c1 e to the -3x plus c2 e to the 3x. Or you can move the yp to the end. Like so. But there was no guessing involved here. So that was a very straightforward one, probably a little too simple. Let's go ahead and move on to another example here. Y double prime plus y prime is equal to 3. So m squared plus m equals 0. M times m plus 1 equals 0. M equals 0, or m plus 1 equals 0, m equals 0, or m equals -1. So my yc is c1 plus c2 e to the negative x. So I'm going to start off with d squared plus d equals 3, and then take the derivative of both sides and get d times d squared plus d is equal to 0. Factor the d out, I get d squared, d plus 1 equals 0. So I have a repeated root here. So I have my y equals a plus bx plus c e to the negative x. So I have this part already taken care of and this part already taken care of. My yp needs to be a constant times x. So yp prime is equal to a, yp double prime is equal to 0. So that gives me 0 plus a is 3, so a is 3, and we have, I'll just call this b, that's okay. So we have y is equal to c1 plus c2 e to the negative x plus 3x, like that. All right, let's move on here to the next example that I have. That is y double prime plus 4y prime plus 4y is equal to 2x plus 6. So auxiliary equation here is m squared plus 4m plus 4 equals 0, which is m plus 2 squared equals 0. So m equals -2, multiplicity 2 is yc is c1 e to the -2x plus c2 x e to the -2x. And I'm going to write this now as d squared plus 4d plus 4 equals 2x plus 6. I'm going to differentiate multiple times here. It's going to show you what's going to happen each time, and then you'll get the idea how many times you need to differentiate. So when I differentiate one time on the right hand side, I get 2. Need to differentiate again to get that to be a 0 on that side. I already have all this stuff here from YC, but this is going to be y equals a plus bx plus c e to the -2x plus d x e to the -2x. This is already in yc, so my yp is equal to a plus bx, kind of like I would have expected there. That's what it looks like. So my yp prime is equal to b, my yp double prime is equal to 0. And I'm looking at yp double prime plus 4yp prime plus 4yp needs to be equal to 2x plus 6. So this is 0 plus 4b plus 4a plus 4bx equals 2x plus 6. So my x parts are 4b is equal to 2, so b is 1/2. My constant parts 4a plus 4b equals 6. with b being 1/2, that means 4a plus 2 equals 6. 4a is 4 and a is 1. So that means that my yp is 1 plus 1/2 x. And that means that my total solution here, y, is equal to a plus bx. I'll put it on the end. And then c1 e to the negative 2x plus c2 x e to the negative 2x. So that is this one here. All right. One more for this video. Again, these are pretty basic examples. Y triple prime plus y double prime is equal to 8x squared. And I don't think that I did one earlier that was higher than second order, but really it doesn't change anything. M cubed plus m squared equals 0. Pull out the m squared and you get m plus 1 equals 0, m squared equals 0, or m plus 1 equals 0, m equals 0 with a multiplicity of 2, or m equals negative 1, multiplicity 1. So yc equals c1 plus c2x plus c3e to the negative x. If we write this as d cubed plus d squared equals 8x squared, I'm going to have to take the derivative 3 times to be able to get this down to 0. One time is going to get it down to linear. Second time is going to get it down to a constant. Derivative of a constant for sure is 0. So d cubed times d cubed plus d squared is equal to 0. Pull the d squared out is d to the 5th times d plus 1 is equal to 0. So my y needs to be a plus bx plus cx squared plus dx cubed plus ex to the 4th plus f e to the negative x. So we already have that term taken care of. We already have that term taken care of and that term taken care of. So my yp here needs to be equal to cx squared plus dx cubed. Again, I don't really like d as a variable because of the differential operator, but you guys get what's going on here. So yp prime is equal to 2cx plus 3dx squared plus 4ex to the 3rd. Yp double prime is equal to 2c plus 6d x plus 12ex squared. I have to go all the way down to y triple prime. So yp triple prime is equal to 0 plus 6d plus 24ex. So I have y triple prime plus y double prime equal to 8x squared. Y triple prime is 6d plus 24ex plus y double prime is 2c plus 6dx plus 12ex squared is equal to 8x squared. So my only thing with my x squared terms is 12e needs to be equal to 8. So e needs to be 8 over 12 is 2/3. With that being the case, I can move back and look at my x terms here that 6d plus 24e needs to be 0 here, and e is 2/3, so 6d plus 24 times 2/3 equals 0. 3 goes into 24 8 times, so 6d plus 16 equals 0, and 6d equals negative 16, and d is equal to negative 4, negative 8/3. Okay, and then once I have that, 6d plus 2c also equals 0, with d being negative 8/3. 2c equals 0. 3 goes into 6 2 times. That's negative 16 plus 2c is 0. 2c is 16 and c is 4. C is 8, excuse me. So that gives me a YP of C is 8, D is negative 8/3, E is 2/3, and that's what goes on the end of Y. So YC was C1 plus C2x plus C3e to the negative x plus 8x squared minus 8/3 x cubed plus 2/3 x to the 4th. Let's check that out. 3/3 x to the 4th, 8 minus 8/3 x cubed, it's 8x squared. All right, so there's your very simple ones where you have just a linear, not linear, a polynomial equation on the right-hand side, and you're just using that differential operator d, but you can see how useful it can be to eliminate the terms that you already have in your YC and know exactly what your YP needs to be. So let's come back and let's do some examples next time with some exponential functions for our second part of this series. See you next time.